There, Mr. Sutton here, bringing you the Algebra 2, Chapter 6, Quiz 1 Review Solutions on Exponential and Logarithmic Functions, Part 1. For this problem, they're telling us that in 2011 the population of some city is 327,000, and during the next 9 years it's increasing by about 7% a year. They want us to use an exponential model to figure out the population in 2020. This model is going to be representing the population t years after 2011, so that's the type of model they want us to set up. Because we're doing population growth, or in general exponential growth, we're going to use our model of f of t equals a times 1 plus r to the t. We're doing plus r instead of minus r because we're increasing rather than decreasing by this amount. So this is going to be an a value, a starting value of 327,000. And the r here is your percentage, so this is going to be 1 plus 0.07. We have to express it as a decimal. And for the t value, well, if we're looking for 2020, that's 9 years after 2011, so we're going to plug in 9 for the t value. And then we'll just go to the calculator and run these numbers. So plug in all this in. We've got 327,000, parentheses, we have 1 plus 0.07. I mean, you could just add that pretty quickly. And then exponent, we got 9. So rounding off to the nearest thousand, it's looking like this is going to be 601,000. And that's how many people we have in 2020 in this city. For this problem, they want us to determine the amount of money we'll have in 8 years if we deposit 25,000 in an account. We're earning 3.5% annual interest, and that is being compounded continuously. The key word is continuously. That tells us that we're going to use our PERT formula for this. F of t equals p times e to the rt. So if we want money in 8 years, we're doing f of 8. Our p value, that's the principal, that's what we deposited initially. That's the 25,000. And the r is the decimal version of this percent increase, so 0.035. So that's going on the e in the exponent there. And then for the t, again, that's the 8 that we're leaving it in there for. Now let's just go to the calculator and see how much money we've got. So we've got 25,000 times e, raise that to the 0.035 times 8. And it's looking like that's $33,078.25 if we round that up. On this problem, I'm trying to evaluate this logarithm. So I'm basically asking, what do I have to raise the base to in order to get the input here? Now, this is ln. This is natural log. So this is really base e, even though we don't write it. So I'm asking, what do I have to raise e to get the 9th root of e squared? And to figure this out, if we rewrite this as an exponent, that might clear things up a little bit. So I can rewrite this as e to the 2 over 9 power over root. And now I'm just asking, what do I have to raise e to get e to the 2/9, and that's just the exponent 2/9. On this problem, I'm trying to simplify 7 to the log base 7 of 64. Well, logs and exponential functions are inverses. They cancel each other out. If you have bases that match here, you essentially are going to cancel out the 7 and the log 7 and just get whatever's inside here, which is 64. To find the inverse on this problem, we're going to start by replacing the y with an x and the x with a y, basically switching those. And then we just have to isolate y. Now, to get rid of this log base 9 expression, one way we can do this is to write this in exponential form. So we would keep the base of 9 as a base, and we would just switch the input and the output. So I'm going to have 9 to the x equaling y minus 4. And then if I just add 4, I've got y by itself, so I can write f inverse of x equals 9 to the x plus 4. To graph y equals log base 8 of x, we're going to start by graphing the exponential inverse of this and then just switching all the x and y values. So the inverse of this is going to be 8 to the x power. And I'm just going to make a table. Since this is a b value of bigger than 1, I'm going to use like my growth numbers, so I'm just going to go from -1 to +2. If this were a fraction that was less than 1, I would use -2 to +1. It just makes things a little bit neater using those points. So 8 to the -1 is 1 over 8. 8 to the 0 is just 1. 8 to the 1 is 8, and 8 squared is 64. So we're just multiplying by 8 each time. Now for log base 8 of x, since this is the inverse of this other function, I just have to switch all the x and y values. So now I've got 1/8, and then -1 is going to be my x value. Then 1 and 0, 8 and 1, 64 and 2. And we'll just graph all this out. When I make my x and y axis, I'm going to leave enough space horizontally to get up to this 64. So I'm going to go by tens here. The y values, I'm just going by ones. So we have 1/8 comma -1. So that's really close to the y-axis there. 1 comma 0 is still pretty close to the y-axis up there. Then 8 comma 1 is around here. And 64 comma 2 is somewhere over here. And there is a vertical asymptote at x equals 0 that these log functions have. So I'm going to make sure I don't cross the y-axis here. So here is my logarithmic function. For this problem, they want us to graph this transformation of the f function. So what is actually going on here? This x plus 2 in here is giving us a translation of left 2. The -3 outside the exponential function shifts us down 2, or down 3 rather. So we're going left 2, down 3. Let me write a parent table for 2 to the x. I'm going to use my exponential growth numbers for x values, so -1 through 2. And I'll just plug each of these into 2 to the x to get my parent table. So 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the 1 is 2, and 2 to the 2 is going to be 4. Now to transform this into the g function, if I'm going left 2, I have to subtract 2 from my x values, and down 3 means I'm doing y minus 3. So subtracting 2 from the x values, -1 becomes -3, then we have -2, -1, and 2 minus 2 is 0. And for the y's, 1/2 minus 3, I can call that -2.5. 1 minus 3 is -2, 2 minus 3 is -1, and 4 minus 3 is 1. And just graphing all that out, we've got -3, -2.5 right here, -2, -2 is there, -1, -1, these are pretty easy to graph, and then 0, 1 is right up here. I do have a horizontal asymptote for these exponential functions. Since I shifted this down 3, my new horizontal asymptote is now y equals -3 rather than the x-axis. So just graphing this all out, here's what we end up with for our exponential function.